Hi, my name is Ashley Hong, and I'm currently filming in Orlando, Florida. And my mentor was Christian, and today I'm going to present about neutron stars and multi-messenger astronomy. So, neutron stars are really exotic, and in 2017, two neutron stars collided and released a burst of gravitational waves, and scientists detected it. So, this event was super unique, which I'll talk more about in detail later. And this was basically the birth of multi messenger astronomy, I'll also explain a little later. So, first, let's talk about some properties of neutron stars. So, neutron stars are the second densest objects in the universe, following black holes, but they're the smallest and densest stars known to exist within the universe. And generally, they're around 20 kilometers in diameter and hold a density of around 3 solar masses within it, which is like 3 of our suns from the solar system. And kind of like as a visualization of their size, a teaspoon of a neutron star can hold up to 10 million tons, which is a lot. And so how they're formed is when a star runs out of fuel and basically like can't maintain hydrostatic equilibrium because their core has fused into iron, so they can't push out against the gravity pushing in. The star will collapse upon itself, and based on the mass of the star, it'll either become a neutron star or a black hole. But first they'll explode into a supernova. So now let's dive in more into multi-messenger astronomy. So multi-messenger astronomy combines information, different kinds of information, for example, like light, cosmic rays, gravitational waves, and neutrinos, to understand more about a certain source they're looking at. So this helps us answer a lot more questions about the universe, such as when we were looking into neutron stars. So different telescopes can observe different parts of the electromagnetic spectrum. But also some objects in the universe don't emit light, such as black holes. So the discovery of neutron stars was in 1967 by a 24-year-old graduate student called Jocelyn Bell. And she found a really unusual source of radio waves, which led to the first gravitational evidence of neutron stars. So neutron stars were a pretty recent discovery, and first being discovered in 1967 because it's really undetectable because it doesn't emit enough electromagnetic radiation because it's so small, which makes multi-messenger astronomy super important in its finding. So LIGO. So LIGO observatories are really unique in capturing information about gravitational waves through these distortions in space-time. So there are a lot of LIGO observatories located throughout the US and other observatories around the world. And so for LIGO, their observatories are made up of two long L-shaped tunnels at an intersection. So there's a beam that gets divided at the intersection and goes down the two L-shaped tunnels, and there's a suspended mirror at each end of the tunnel that reflects the light back into each tunnel. So I have a picture and you can see if it helps you visualize it better. That the laser beam should return to the spot where they were split exactly at the same time if there were no gravitational waves. But however, if a gravitational wave passes through the observatory, it changes the beam's arrival time. And the change is so small, but it's still detectable by LIGO. So this really complex arrangement observatory kind of demonstrates how accurate you need to be to detect these gravitational waves. So researchers have found evidence of light and wave ripples in space-time at around 70 ground and space-based observatories. So the first detection of the gravitational signal from neutron stars, the wave was called GW170817, and this occurred on August 17th. So the objects that LIGO and Virgo discovered were these two objects just going around each other. They were spiraling around each other, and the size was they were smaller than binary black holes, but around 1.1 to 1.6 times the mass of the sun. So they were around the size of neutron stars. And so they discovered two binary neutron stars swirling around each other about to merge, which is what was um, spreading out, which is basically where the gravitational waves were coming from that they were discovering at LIGO. So, in conclusion, our knowledge of neutron stars increased a lot with the combination of different pieces of information from multi-messenger astronomy, like electromagnetic measurements, gravitational wave detections, things like that. And the 2017 collision of neutron stars really showed how that was really important in discovering things in our universe. So it also all the observatories working together trying to solve the mystery of the binary neutron stars really demonstrated global cooperation and also offered new information on what happens following these kind of cosmic events. And so looking ahead, multi-messenger astronomy has so much potential in advancing our understanding of the universe by answering unsolved questions about the most mysterious phenomena that have ever existed. Thank you.